Today is quantum mechanics and its interpretations. So, I'm a physics minor. I'm taking quantum mechanics 2 right now with the ML car over here. And when I first started taking quantum mechanics, I was really expecting it to be a lot more complex and like esoteric than it really was. I didn't think I'd be able to understand it. In the beginning, I really didn't. But on the first day, did you take it with Wei?
Yeah.
Yeah, on the first day, he says something like no one understands quantum mechanics. Like sometimes you just get like a little bit less confused. And since then, I feel as if I've gotten a little less confused about it. And so I would like to help you guys get a little bit less confused as well. So yeah, I hope you enjoy. I intended this to be almost like a 50-minute lecture, similar to what you would encounter in your like normal classes. But I have a feeling that's going to run longer than that. So I hope you'll bear with me. I'm a little bit under the weather as well. So please give me a little bit of grace. But let's get started here. So before we can talk about quantum mechanics, let's first take an adventure into classical mechanics, which is probably what most of you are familiar with, having taken like physics 2048, 2049. So I want to illustrate it so that we can then distinguish it from what quantum mechanics is. So in classical mechanics, things are inherently deterministic, right? If you have a certain amount of information about a system, you can always tell what it will be like in the future. So for example, if you have some particle and we know all the forces that are acting on it, we can then predict where it will be in the future at some other time. So examples of like classical mechanical laws would be like Newton's laws, conservation laws, and in classical mechanics, objects have definite positions and velocities, right? And we can understand the paths that they have through space and through time, right? In classical mechanics, it's very easy to tell like what's happening to a particle at any given time, because the only things that can affect a particle at some time are those which are directly in contact with it. And that's what we call local causality, right? And in comparison to quantum mechanics, classical mechanics is like very physically and mathematically simple to understand. The reason we learn about classical mechanics first before quantum mechanics is because classical mechanics apply to macroscopic objects, so things that are relatively big, at least compared to like, let's say a point particle. Also in classical mechanics, you'll always observe continuous observable values. So when we're talking about, for example, position, right? Position exists on a continuum, right? It's not discrete in that there's only one or two possible values, right? If I'm on the number line at 0 and then at 1, the real number is there's an infinite number of values between 0 and 1. It's a continuum. It's not just 0 and 1. And classical mechanics started in the 1600s with Isaac Newton. So now let's go into quantum mechanics. So quantum mechanics as a theory has many different interpretations, and the primary one you'll learn about if you're taking like quantum mechanics here at UF or basically anywhere, the most orthodox interpretation is the Copenhagen interpretation. So the Copenhagen interpretation of quantum mechanics is an inherently probabilistic theory. So in classical mechanics, we can know exactly the positions and the velocities of particles, but in quantum mechanics, we no longer have that. In classical mechanics, we had like Newton's laws, which gave us these definite values, but now all we have is a probabilistic understanding of particles, where they are, what their observable values are, how fast they're going. An example that illustrates this would be something like Born's rule. Again, with the indefinite positions of velocities, this is illustrated greatly with Heisenberg's uncertainty principle, which I will get into more later. In classical mechanics, we had local causality, which made it very easy to tell what was happening to a particle. But this doesn't hold in the Copenhagen interpretation of quantum mechanics. Now we have non-local causality, where two systems that are at different places that aren't directly interacting can still have influence over each other. And again, due to the probabilistic nature of quantum mechanics, we can no longer make definite predictions. It becomes unpredictable. The nice part about quantum mechanics is that mathematically, it's very simple, like relatively simple. But the thing is, physically, in reality, its consequences are like pretty disturbing. So it becomes a task to reconcile those. And as classical mechanics applies to macroscopic objects and systems, quantum mechanical effects are only really observed on the microscopic level. You have to go to very, very small spaces and times for these effects of quantum mechanics to become evident. And quantum mechanics, the Copenhagen interpretation at least, started in the 1900s with scientist Max Planck. Yeah.
I wanted to ask, so are you jumping straight into the interpretations?
You can't really separate, there's no objective like theory that is quantum mechanics.
Okay.
All you have really is different interpretations of the same phenomena that is like experience. So these experiments are performed and these results are shown, and people will interpret those results in different ways. So the Copenhagen interpretation is the most orthodox one, the one that is most widely held by scientists, and that's what I will use to introduce most of these quantum mechanics concepts and experiments before then looking at the other interpretations.
Okay. No, yes, thank you. I was curious because I would love to hear more about like the origin of quantum mechanics. Like from my like background knowledge, which is very little, doesn't this like come out of the debates of like what's that like Danish guy? What's his name again?
You'll have to be a little
He liked Kierkegaard. He liked Kierkegaard. He came up with like that. Like I think it's Niels Bohr.
Bohr.
Like what's the story of like you say at the very bottom here started with Max Planck. What's the story of this guy? Like did he like reach some massive contradiction by which he tried to create a theory by which whatever contradiction he saw was intelligible under this way of understanding things? Is it like through them trying to become more and more microscopic, they're like developing quantum? Is quantum the only way to measure like microscopic scales? Like, is there other theories? Is quantum one thing among many? Like, I'm very curious about all these questions, so I can have just a bit more context as to like.
Do you think I could get to these questions later? Is that okay?
Like at the end or like?
Probably towards the end, because it's not exactly the most relevant. This presentation is intended to provide like the background knowledge for like more an educational perspective of quantum mechanics rather than a historical perspective. So I think maybe saving that towards the end would be better, or maybe after the presentation, if that's okay.
Oh, yeah.
Yes, the other question?
Just so I can jump in, I think the reason that all of this started was because of this double slit experiment.
Yeah, I'm going to get to that here in a second.
Yeah,
Did that like blow everyone's mind?
yeah.
There's a lot about the double slit experiment, so we'll get into that. But yes, essentially, these experiments, the results of these experiments indicated that the incompleteness of the classical mechanical theories. So when you start doing experiments at these microscopic scales, that's when we start to see these weird results, which are then explained using quantum mechanics.
Oh yeah. Can I ask more question?
Sure.
Obviously, like the biggest name you hear today is like, and then it's literally a proverb. That guy's an Einstein.
Yeah.
He's a big guy in physics, right?
Yeah.
Is he like only concerned with, or like I guess principally concerned with the macroscopic level? Like
No, Einstein was one of the first people to talk about quantum mechanics. He actually rejected this Copenhagen interpretation. I'll get into that later.
Okay.
You'll see a lot of the history as I go through this presentation. I can get a hand over here.
It's fine.
No, you're good?
We can talk about it later, it's fine.
Okay.
I don't want to, I just go.
Okay. And yeah, feel free to like raise your hand if you have questions or I need to explain something more, feel free. Just let me know. Alright. So, in the Copenhagen interpretation of quantum mechanics, there's this concept of a system's wave function. So, a wave function is basically the only real representation of a system that we can know, right? The wave function contains within it everything that we can possibly know about some system. So a system could be a particle, it could be an atom, or a combination thereof. But if you add too many, you start entering the macroscopic level, and the quantum mechanical theories start to fall apart. You actually, as your system gets bigger and bigger, the quantum mechanical theory approaches the classical mechanical theory. So they're not exactly like in contradiction. That's right. But what's important to note is that this wave function is like a purely conceptual entity, right? We don't actually see a wave function anywhere, right? But what we can observe about the wave, how we know about the wave function is through its square modulus, which is actually a probability distribution that will kind of give you information about where the particle could be in space. So, for example, this board's okay, right?
Yes.
So we'll call this x, and this will be, let's say we have a wave function that looks something like this, right? So we can see it oscillating up and down. But what happens is, if this is our psi, our wave function, if we take the square modulus of it, we'll get something that looks like this. And this right here represents the probability distribution of the particle. So this is position 0, and this is the and this represents the probability of this line. So I guess here it's like probability of the particle being at this position. Like, can you guys see from this where the most likely spot to find the particle is? The origin, right? It has the highest probability density at this point. So this probability distribution is what we can actually measure over repeated experiments, and this is actually what we can know about the system. We can't actually know this wave function in and of itself. Mathematically we can, but physically we cannot observe that. And as for the reasoning of why we have these wave function, like why are they waves, you'll see here in a minute when we talk about the double slit experiment. So this slide I was hesitant to include. It's very jargony. It's a lot of the math. It contains a lot of the math of quantum mechanics and observables, and I don't intend for this presentation to be super math focused. So it's not that important. So I might come back to this slide later. But yeah, basically the big takeaway is that if we have a wave function and we want to extract out some information about the system from it, like for example its position or its speed, what we do is we take these wave functions psi and we apply some operator to them. And this operator is just like a mathematical transformation which takes in the wave function and it returns a value. And what that value is the value of the observable. So if I use the observable operator for momentum and I apply it to a wave function, the value that I get out will be the momentum. But this will be illustrated more later. So the Schrodinger equation. Schrodinger is a name you've probably heard a lot in relation to quantum mechanics. The Schrodinger equation is a fundamental equation that describes how these wave functions evolve over time. And basically, it's what provides the constraints for what can be a possible system and what cannot be. So wave functions for valid quantum states satisfy this equation. And this equation has a time-dependent form and a time-independent form, depending on if the forces that are acting on the system are changing over time or not. So I have this short 60-second video that explains it a little bit, so I'll play that here.
The Schrodinger equation is the key equation in quantum physics that explains how particles in quantum physics behave. You want to know where your electron's going to go? That's the Schrodinger equation you'll need. So why does it look so complicated? Well, it's because in quantum physics, when you're describing what a thing like an electron will do, it doesn't follow the rules of particles, it follows the rules of waves. And that's what these psi's are, they're wave functions. Okay, so an electron is a wave, and a wave can evolve in space and in time. But it can't evolve in any old way. There are constraints about how it can evolve, and those constraints, that's what the Schrodinger equation is telling us. It says that over time, that's this bit, the total energy has to stay the same. And this total energy is made of the kinetic energy, that's this bit, and the potential energy, that's that bit. An example for a potential energy for an electron is just being in an atom. So if you want to see what a quantum object will do in the future, you need to find the wave function that will satisfy all of these bits of the Schrodinger equation.
So there we go. Basically, Schrodinger equation just says that the total energy in the system has to remain the same. It's like a quantum analog for conservation of energy.
The Schrodinger equation is the key.
Okay, now we enter the double slit experiment. As you can see, very important experiment. You'll probably learn about it first in modern physics, but it's of vital importance when you start learning about quantum mechanics. So the reason why we have this idea of a wave function is that particles behave as both particles and waves. So that's where we get the notion of wave-particle duality. And the wave-like behavior of particles was revealed in the electron double slit experiment, which was first done, I think, with electrons. I think it was before 1961, but I couldn't find a source before that, so I just put 1961 here. But it was first done with light, a similar double slit experiment, in 1801, which actually showed the particle-like nature of light waves. So the setup is as follows. Sorry for people on this side. If you can't see, you might need to move.
Yeah,
I need to, like the way they design this building, like they have the screen comes right in front of the middle board, which doesn't make sense. But I'm just going to be drawing basically what's up there. Essentially, what we have is we have a gun that shoots out these electrons onto a screen that has some slits in it. And then what we do is we observe what happens after they go through the slits. So this is just what the setup is. So then we first start with seeing, okay, before we get into the double slit, what happens if we have just one slit and we have a bunch of electrons going through? So what we'll see on the screen where we're observing where the electrons are ending up is you'll see kind of what looks like a normal distribution if you're looking at where the particles are and like the amount that are there, which is kind of what you'd expect. If you just have a hole and the electrons are going through a hole, they might like move a little bit away from the center of the slit, but in general it'll follow a normal distribution. It's kind of what you'd expect, and this is what we predict. And if you have the other slit open and close the first one, on the other side you also see that same normal distribution, but it's now centered around that second slit. The interesting part is what happens when we have both slits open at the same time. So if we have both open at the same time, what you predict is that it would just be the addition of the two individual slits. So we'd have a distribution that looks like this, right, with a bunch of probability that's centered around where the top slit is and where the bottom slit is. Just two normal distributions added together. But in actuality, that isn't what we observe. What we observe is an interference pattern, the type that arises when we add two waves together. So if you have two waves and you add them together, at some points they're going to have constructive interference, where they add together and get bigger, and destructive interference, where they cancel out and get smaller. And this is what we observe when we have both open at the same time. Because if we consider them classically as distributing as particles, we'd expect to just get this double distribution. But if they are acting as waves, what happens is that as they go through both these slits, these waves come in contact and they have this interference with each other. And we can see that by the way that the distribution looks on the screen. So experimentally, this is what was observed. And there isn't any classical explanation for this phenomenon. But if you consider the particles to be waves, it makes pretty good sense. Yeah.
It's just like a simple, just experimental question.
Yeah.
For the detector, are they just determining like just intensity, or are they accounting for energy in terms of what's incident on the detector?
I think it's just intensity.
Okay, so that wouldn't impact.
It's number of strikes.
Yeah.
Yeah, that wouldn't impact. Never mind. I'll ask later.
Okay.
It's just I'd have to read the paper.
Yeah. So then the question comes is like, okay, well I've just established in Copenhagen that everything is a wave, particles are waves, but like when we look in the world, we don't just see a bunch of waves, right? We see particles, we see actual things, right? We see them being in a place at a time. So the question becomes like, when do particles start acting like particles? And the answer is when we start looking at them upon observation. When we observe a system, that act itself will collapse the wave function, as you can see here. So when it collapses, we can see that the probability spikes at that position, and that's where we'll find the particle. Yeah. Question?
Okay, define observation, because like I'm sure it's not just like the fact that my eyes are looking at it that it changes.
Yes, right. So that is one type of observation. If you were like looking at its position, but it could be like a measurement of the energy of the system. It could be any type of measurement. Anytime you're extracting information out of the system.
So when you collect the data and I guess look at the data properly, don't collect.
Yeah, as soon as the information becomes available, right? As soon as like something is known about it, it changes. Do you have something to add?
I wanted to add on to like the
Go ahead.
answer of that. It would be like when another particle interacts with it, you have observed it. Like if you see it, a photon has interacted with it, so you could reflect it. If you were to measure something on it, you would have to do something to it to measure it. So it's like the interaction with it makes it observed.
Can you say that? So you're saying when the photon hits it,
It's become observed.
isn't the photon already hitting it though?
Not if you're not looking.
Not
Like it
reflected.
hasn't reflected and you had to hit your eyes.
Why does like the photon's hitting it? Why don't they like look at it for the photon to hit it?
Yes, because the photon's bouncing off of your eyes.
the photon that hits your eyes has hit it and bounced back.
Yeah.
Yeah, the photon is how you're looking
Photon's
at
just
it.
like light.
Can we
Yeah.
say, can we table this?
Yes.
Well, this is like the interesting part now. I would love to get into this.
Do you have what's your question?
So my question, and again, if this is like beyond the scope or something we should say to the end, do not feel bad for doing that. But I just have to ask because I'm like finding an analog in, I guess like epistemology with this is like, there seems to be, like with this collapsed and unobserved kind of dichotomy, there seems to be an analog with things which are in themselves and for consciousness. That is, things that are, like what a thing is essentially in and by itself, like what it would do left on its own, to its own devices, and what it is for consciousness. Like, and this is like a very popular distinction within certain realms of philosophy about like, well, how do we speak things in themselves if we only observe them for consciousness? And then there becomes a later question of how can we even posit that there is such a thing as a thing in itself and not for consciousness? It seems undivorceable.
Yeah.
So to apply that to this, how is it posited that there is an unobserved state, and how can you like predict what it would look like if by nature it is unobserved?
So how do you see like the wave function before observation?
Yeah, like
So-
how do you model that?
Yeah, so the answer is it's a probability distribution, so like repeated experiment, right? So you do a bunch of these measurements for a system over time, and the results, you'll get varying results every time, and you'll see the distribution that comes out of
But
it.
that would be after measurement, though. So that would only tell you things about its observed. So I'm not.
But I assume it would collapse differently in accordance with
Well,
this. Just
you'll- You'll
Okay.
see the mathematical
It's like a
representation of what it is
Okay.
before, here in a minute.
Okay.
So by the end, if it's not answered, then we can come back to
Okay,
that.
okay.
You have a question back?
Yeah, what is observed, how come it's still kind of, a probability distribution rather than like
Yeah.
a step function? Is that have to do
Okay,
with the
so
fact
this
that
this
observing
is
it
a
in
bad
person?
this is a like kind of a bad image. In reality, it's not. This looks like it has like some finite height, but in reality, it's a delta function. So it's actually the probability density is infinitely spiked at that point, and because like here, if we're looking at position, for example, that's a continuous range. We have like an infinite amount multiplied by an infinitesimally small amount. This normalizes out to be a probability of 1. So it's a delta function, even though it doesn't look like, it looks like it has some width. Really, in reality, this is infinitesimally small.
Okay.
Does that answer your question?
Yeah.
Okay. Okay, so now we can think about the double slit experiment, but instead of just letting it do its thing, what happens if we add a camera to one of the slits so that we can see when the electron passes through it? Without looking at what's there, do we have any idea about what happens? If you add a camera looking at one of the slits.
The photon has now interacted with it.
And what does that mean?
Therefore,
It
it's
changes
not, it no longer
position.
behaves as a wave.
Okay, so what does that look like on the screen? What does that do?
Before, when you had the probability distribution area kind of fringe.
Two bumps.
Yeah,
Like just
that.
here
There and twice.
and twice, right? Because even if we don't see it going through here, right? We know that it's going through here, so that's still an observation, even though we're not looking at it. We're still gaining information out of the system and collapsing the wave function.
I have a question. You
Yeah.
call me a dunce, but I'm still not understanding. Like, is the camera causing the photon to hit it?
So
Are the photons
this question
already
is like
hitting
a fundamental question of quantum mechanics.
Okay.
Like,
That's all you have to say.
no, yeah,
It's a true
okay.
form of woods is like. if-
Yeah.
Well, there's an answer to that. There's an
Yeah.
answer to that.
So,
It's the same- it's
so
not the same
that,
question.
the photon, like that's a theory, like that's one of the theories, that's what's, there is some interaction happening, but like the act of observation, it's like a non-linear, like,
It's an act. It's not like operating in isolation.
yeah. So the question of like, why does measurement do this? That's like the fundamental question of the Copenhagen interpretation. And it's not even their question, they actually just reject it. They don't want to answer
Are
that
you
question.
equating like photons with measurement?
No, I was saying that, I was saying that in like response, because he mentioned that.
Okay. That's
But
another-
I don't think that's all measurement is. Go ahead.
Is there a movement on like the experimental side now trying to develop detectors such that you can try to minimize that issue, or is that merely
What,
just
do you- what
possible?
issue?
Of like, now you're detecting it, now you're impacting it. Like, is it possible you could get a detector that was like,
Remove the
No,
influence.
this is the.
Yeah.
No,
effect.
this is the
Like a
fun,
thing
this is
that-
like fundamental
So you
to
just-
quantum.
okay?
As soon as you're
okay,
extracting
around it?
information out of it, you're collapsing the
I
wave
like that
function.
question.
This is
Okay,
unavoidable.
I just didn't know if there was like any experimental answer, because it sounds as if you just kind of like put yourself in a, if you don't have any experimental empirical proof, then you just have theory, right? To get around it.
Experimental empirical proof of what?
To be able to observe it and to like change the theory, if you are then saying that like you can't, I don't know. I'll just wait till the end. We
Okay.
can talk about that later.
What he's saying is like you encounter something that's unintelligible, so you have to make a new theory to like describe the unintelligible.
Right,
He's just
so-
asking,
so-
can we just make a new
This
experiment?
is where we enter the different interpretations of quantum mechanics. So this is illustrating the phenomena that was that was observed experimentation, and then quantum mechanics, the different interpretations came as a way to answer and explain why that is. So the thing is about Copenhagen is they actually would just like reject the question of like, don't worry about measurement. They actually just reject the question entirely.
But isn't that how this arose? So like that's why, like, don't you need a communication between theory and experiment? Isn't that how you move like, or sorry, theory and experiment? Isn't that how you like move the needle? Like I thought that was.
Do you think we could come back to this after
Yeah,
the
I'm
presentation?
sorry.
Okay.
I'm sorry.
No worries.
Just to read the paper.
It's just, yeah. Like, quantum mechanics is such an interesting topic, there's so much to talk about, that, like, I could spend, like, 2 hours just talking about the double slit experiment. But, there's a lot to cover, so, I suppose we should move on. Okay, so then, this is kind of the question we're talking about. So, like, we have a system, and we measure a particle to be in some position, call it x naught, at some time t naught. And then we ask the question, where is the particle before measurement, right? So, there are some possible responses you can have. So, a realistic response would be to say that the particle was like always there, but we just had no way of knowing that, and that's what the wave function is. It's just a representation of our not knowingness. But what the Copenhagen response would be to say is that the particle was actually in all of the places it could have been simultaneously, and that's the principle of superposition. Something being in multiple states at once. And then you can also just say like you don't care about where the particle is before measurement, because it's like it's before measurement. Why would we care about something before measurement? Go ahead.
Now, is superposition saying that the reality is that it is in all those places, or that like statistically it could be recognized as being in all those places?
Well, statistically, it definitely can. Mathematically, it works out perfectly. But yes, this is a question of reality. Like this is the whole question. This is where there's no answer. There's no answer to this yet. Go ahead.
So that I can understand more of you in the presentation. Of these 3 responses, where do you fall?
Like the realistic one.
I don't think I'd fall in any of these.
Then where would you fall?
Yeah, I think. Well, maybe not. I would just say I don't know.
Catholic.
I don't.
So purely just like
I don't have any personal feelings about where particles are.
You're kind of like 3. Secretly.
Yeah, I guess so.
Ooh, we caught it.
Interesting.
That's a secret fourth one.
There's a secret fourth one that encapsulates all the but like better. Okay, go ahead.
Okay, so I
It's
kind of to
superposition of all
grab
things.
onto my earlier question, so is superposition not something that's ever directly observable? As in like, it is something that we have ascertained?
You'll see how it's observable. I'll
Oh,
demonstrate.
oh.
You'll see. Well, no, I'll mathematically show you
Wow.
how it comes into play.
You'll write it out?
Yeah, go ahead, Massimo.
So the superposition principle, it exists everywhere simultaneously. Yet again, it's just a wave, right, existing over some space. But it exists as a wave until we can observe it and measure it, and then
Well, this is-
there's a Heisenberg uncertainty principle with that measurement.
Well,
So is it like an equally valid response to like just say like it doesn't exist realistically? It realistically doesn't exist until you look at it.
yeah, and actually,
It's
like,
superimposed, so really it doesn't exist
that's
until I
yeah,
like
I
consciously
you could
materialize
say,
it.
and some people would say that. Actually, that's probably closer to what I would say.
Yeah, okay.
But that ties into like my personal
Pure being,
belief.
pure nothing.
That's
like
right.
Yeah.
magic.
Okay.
But yeah, so that's also a valid response too. But most of the time you'll see one of these 3. Most people wouldn't say it just doesn't exist because they're scientists and they believe in like an objective reality.
Right, okay.
Go ahead.
How do you see the orthodox response of its orthodox developing?
Should be lowercase.
Sorry.
Like, how do you see that response developing in terms of like, if it is the current like accepted view, how do you see it developing and changing over time as interacting with these others? Like, how do you see it changing?
I don't see it. What do
You
you mean by
think-
changing?
Like he's asking, what's the history of the Copenhagen interpretation when it's forced to like justify itself to the other interpretations that are emerging?
It
Yeah.
isn't
How to
like a
become one.
historical, like it's like a necessary, like fundamental axiom of the theory.
Isn't it a
It's a-
school?
it's a-
It's a school of thought.
No, the orthodox
Sure.
thing is the theory of quantum mechanics. There is no other when you're taught it, you're taught this.
But
So there's only one interpretation. It's Copenhagen.
Aren't there like
When you're
different?
taught, you're like,
aren't
this
there
is it,
different?
this
I'm
is,
sorry.
we don't
sorry.
know
Just
what-
continue. I'm sorry.
Don't apologize.
No,
We're
it's
just
just
like we're here to learn. We're here to learn.
It's just he's trying to get through it. It's
No,
it's
no,
it's
no.
okay.
learning.
This is
Okay.
fine.
Good.
My goal here is to give you guys information. So whatever you guys need
Yeah, you don't
to extract the most information. I appreciate the questions. So keep them coming.
Okay.
So
I don't know if I can
everything
answer them all, but I'll do my best.
Everything else will not be quantum.
Sorry?
It won't be quantum if it's not Copenhagen.
No.
What is it
You
called?
know,
then?
Oh, never
A
mind.
different interpretation of quantum mechanics.
Okay, so it still is
You
quantum.
have a back.
It still is quantum.
Well, that goes against what Masu was saying.
What I said?
I didn't hear what Massimo was saying, so I can't.
They're all
defend it.
quantum. What do you mean?
I completely missed it. I'm sorry. I wasn't listening.
You gotta listen.
My bad.
Are we good? Can we advance? Okay. Sebastian, I did not know you're so interested. I should have brought this up way sooner if I had known.
You were just saying like
What was it?
the Copenhagen interpretation is quantum mechanics,
Yeah.
which would imply that
It is-
something that isn't the Copenhagen interpretation isn't quantum mechanics.
So when you're taught quantum mechanics, if you take physics 4604 and 4605 at UF, you will learn the Copenhagen interpretation exclusively. You will not really learn about the other interpretations at all.
academic document.
It is the most widely held theory by in the state of science of academia
That's why
today,
it's orthodox.
and that's why it's orthodox. Go ahead.
Do you agree with the like that, or would you rather that they taught all of them? Like going through the class?
Well, the Copenhagen interpretation, I think, has the most predictive power. As a tool, it's the most useful in describing these quantum mechanical results at this time. I don't think it's like completely correct, though. But I don't think that they should change the way that they're teaching it. I mean, you have to add a different course, maybe. Go ahead.
I ask you this because I anticipate that this will probably be one of the next slides, and I want to give you a chance to do that. What is the what predictive power does the Copenhagen interpretation give us? Like superposition, the principle. Like, what predictive power does that have? Because you said before that you could demonstrate it mathematically, but again, mathematics is still kind of abstracted. As far
It's
as
just
empirical-
said statistically. You'll observe it, not just like mathematically.
Okay.
Like you'll see the statistical reality behind its predictions
That's what you said.
in experimentation.
Yeah.
You did answer.
Yes, I'd like to see.
Okay.
Let him cook.
Yes.
But yes, let me cook. Okay, so then now the second question would be, let's say we just finished measuring the particle. It was at position x naught times t naught. Where is the particle if we measure it at some time t1 that is like directly after the first measurement? Without looking at the answer, do we have any answers? I thought I put a slide to like separate them, but maybe
I'm
not.
trying to like not give the answer.
It's too late.
It's everywhere. It's everywhere.
Wrong.
Wait, no, wait.
My
Wrong.
computer.
Wait, no, because we measure it. Dang it. Oh, dang it.
Okay, so where is it?
It follows standard distribution.
Wrong again.
Okay, sorry.
No,
Again.
I haven't taken these classes.
that's why I'm here. So, if we've measured the wave function, what has happened, right? What have we been talking about?
You've
It
collapsed.
collapsed. So what does that look like?
Standard deviation.
It's
No,
infinitely in
infinite-
the one spot.
Oh,
The
right.
delta
It's
function.
So it always
delta
has to
function.
be in
Is
the
that
right
on there?
place.
Delta function on there?
What?
Is that like a?
The delta function is
No,
not-
that's separate. I'll get to that. Okay, so then this is after the first measurement. And the wave function now looks like this. So measure it again. This
Be
is.
somewhere else.
Are you sure?
You're trying to make me doubt myself. I'm doubling down.
Okay. Anyone else besides Chase?
Oh, okay. You're trying to tell someone else.
Where's the particle, Sarah?
I have no idea.
Particle,
Okay.
yeah.
I can tell you the answer though. I think
At which the initial revolution, right?
Yeah.
Correct.
I think it's
Okay. Right. So we had our wave function. We observed it. It collapsed to this. This is now our probability distribution. It has an infinite probability density at this one point. You're gonna find it at that point again, 100% of the time, right? So wave function has collapsed.
always at the same point at the same
Well,
time?
after observation, and not always. Sorry.
Okay.
If you measured it immediately after, if you do one measurement at time t0, and then after an infinitesimally small amount of time, you measure it again at t1. At t1, it will always be at this point, right?
So is this not like, so I assume that T0 or T2, for example, it would move, it'd be infinite.
Right. So here,
So
after
is
some
this
amount
a
of time.
measurement of transmission, like of actual motion of the particle?
Sorry.
Like, but is this not just measuring like how it's moving?
Well, no, because this is a probability distribution, and even if, like it collapses here. It could have been at any one of these spots, but then during the act of measurement, it definitively comes to this spot, right? This doesn't just describe the motion of the particle.
No, I know, but
Okay.
like, if you're observing based on like progression of time, is it not the particle moving into different places at different points in time that you're seeing this collapse and moving?
So this,
Like, if I shoot a bow and arrow, right, and I shoot my arrow, and at 1 second after the arrow is in one location every single time, if I use every other parameter identical, but then a second after that first second, it would be somewhere else every single time at the same.
right. So yes, so it would change.
Yeah.
So what happens is that the wave function will then evolve according to the Schrodinger equation. So after some time, if this was the original distribution and then spiked here, after some time, it'll go back to looking like this, if it's not being observed, due to like the natural like entropy. And again, according to the Schrodinger equation, it'll revert back to this wave function.
Okay.
And then if you measure it again, it might spike here at a different point than where it initially spiked. Because the probability distribution has then, like, it's spread back out and it has some probability to be at this spot again. But it will never go from being here to here, right? And that's actually represented because this probability density, interestingly enough, it flows. It flows like a liquid and it's governed by like the continuity equation. Emilcar, do you remember the continuity equation?
Partial U, partial T is equal to C squared, partial
It should be like partial J, partial X equals partial C.
Yeah, it's
Over
C
partial-
It's
squared.
like the amount.
It's a second partial derivative.
It's a second?
Yeah, second partial.
Are you sure?
I just did it, yeah.
Okay.
And it's C squared times the partial with respect to time, and then partial with respect to X, and then partial with respect to time, and C squared over time.
Yeah. Okay. I just remember. But if you look at this
Yeah.
GIF here, what you'll see is that this is
GIF?
GIF.
No, GIF.
It's GIF. The creator of it said it's GIF. Bro.
GIF.
No, you're the creator.
No, you can do
God, is God wrong?
There's no way you said
False and different question.
No, it's not. The man that made okay, here. Yes.
So just to clarify, make sure I'm tracking with this.
Yeah.
You always define where the particle is by the act of observation every single time.
I don't like the word define, but you cause it to collapse to a point. You don't choose. You can't choose. I can't choose to make it collapse to a certain point.
Right, but the
I can
act
make
of
it collapse,
observation
but it's
is
gonna
what's
collapse.
causing the collapse every time without fail.
Yes.
Okay.
Well, according to the Copenhagen interpretation.
Right.
You'll see other ones that
We don't
say
want
otherwise
this.
later.
At the very least, it's correlated.
We prefer Singh.
Do we have? I think we have. No, you're good.
Yeah, the second one, guys.
Okay, cool.
It's good.
Okay, so now talking about. Okay, I have to start talking about this slide.
It's on the last slide. Can you
Okay.
clarify what suitable? Can you clarify what suitable time means? It's in
Yeah.
quotations. Can you elaborate?
Yeah, well, suitable. It depends on the system. So it depends on the time for it to go back to normal.
But like what in the system is dependent on? Like there must be
The
something.
complexity of the system. Like there's a bunch of different factors. That's why I put it in quotes.
Like is it based on like position? Is it like there's other things in the system?
Yes, it's based on all of those. It's based on all. It's based
So
on
it's
all
just
of
as a function of just infinite variables that is just infinite complexity. Then I
Yeah, yes. The wave function is an infinite dimensional complex vector.
Okay, so
So yes.
it's unfair. Okay.
Go ahead.
Yeah, this isn't a question, this is more so a comment.
Go
But this
ahead.
is the basic idea behind what's called the quantum Zeno effect. You remember
remember
that.
that.
So basically, yeah,
That's what
if
birds
you,
use, right?
yeah, if you make successive measurements quick enough, the wave function won't be able to evolve.
Yeah.
And so you'll just get the same result each time.
Right. So yeah.
Yeah, it is.
Zeno's paradox.
That's Zeno's paradox.
Yeah.
Pretty
Pretty
good.
much,
I didn't
yeah.
know that. That's cool. Okay. Any more questions with this slide before I move on? Okay.
I understand.
Now we can finally start talking about superposition. And you guys probably know about this through like the example of Schrodinger's cat. I'm sure everyone's heard of Schrodinger's cat. I found this picture on like Google Images, and I was like, bro, this does not look like a cat. So that's why I included it. But
Schrodinger's cat.
but yeah, so basically what the principle of superposition says is that a system can exist in multiple quantum states simultaneously, right? That's why the Copenhagen was that it's everywhere, because it can be at all of these positions on its probability distribution at the same time until you measure it, and then it's at one position. And this principle of superposition is mathematically shown through the fact that the Schrodinger equation is a linear differential equation. And what that means is that if I have two solutions to the Schrodinger equation, psi 1 and psi 2, then A psi 1 plus B psi 2 will also satisfy the Schrodinger equation, where A and B are complex coefficients. So that means that this will also be a valid state. So we can have these quantum states and we can add them together in different ways, and those will also be possible states. That's like the mathematics of it, and that's how the superposition principle is represented in the Copenhagen interpretation. And to that line, so let's look at the Schrodinger's cat example. So in Schrodinger's cat, we have is like you have a cat that's like in a box. This is my, I don't know why I looked at
What
that.
is that?
It's a cat. It's a cat.
So
And
it's a caterpillar.
I think the classical one, my physics people, was it like an atom decay that determines if
It's a radioactive decay particle.
Yeah, okay, so there's some like particle in the box too, and after some time the particle will decay, and then if it decays, then it like shoots a gun at the cat. Or like it releases poison and kills the cat. Right? But it's in a box, so you can't see any of this happening. But if you wait over enough time, you'll know that at one point in time, you won't know if the atom is decayed or not, and if the gun is fired or not. So if you're just looking at this box from the outside, then the cat could in quantum mechanics be considered to be in a superposition of dead and alive states. And it is only when we open the box and look at the cat that we can know that it's dead or alive. But according to the principle of superposition, it can be in a state of both dead and alive at the same time. And let's say that the probability at the time, there's like a 1/2 chance that the gun shoots and it dies. So we could represent that, the wave function for this cat as, it would be 1 over square root of 2 times dead. This is going to be our state, plus 1 over square root of 2 times alive. That's hard to see. But yeah, so dead is a solution. It can be dead, it can be alive, but to satisfy the superposition principle, before the measurement of opening the box, this is the state of the cat. It's like half dead, half alive. Not actually. It's both dead and alive. And it has a certain probability of being dead or alive, which is given by Born's rule, which says that if we have this wave function here, that's a linear combination of these states, dead and alive, then if we want to know what the probability of it being dead or alive is, it's given by the square of these coefficients that are next to these eigenstates.
That makes more sense.
So that's why it'd be 1/2 probability dead, 1/2 probability alive, because it is the square. If this is our A value here, then it's actually absolute A squared gives us a probability. Because it's complex coefficients, so you have to take the square modulus.
Of course.
Yeah. Yes.
So this is like abstracted to all particles, right? The cat being the particle. Like
This is just a very simple way to like explain the principle.
It's true, yes. No, but I'm saying like now imagine we had an electron orbiting, an atom.
Yeah.
Now the electron wouldn't follow the classic Bohr model like orbit. It would like be an electron cloud, like in the cloud representing the probability distribution of where the electron might be.
Well, I mean the energy is quantized and according to the Pauli.
Well, yeah, but it's like it's a level of electron gas and it exists.
It can be in a superposition of like a ground state and an excited state. Like that's possible.
Yeah. So I was saying like I'm just going back to my point like before, like does the atom, like, does the electron even, like, is the electron isn't a particle really until you look at it. The electron like never is a particle.
Well, it still has effect, even if you don't
It
like.
still has effect, but it has like a wave effect.
Sorry.
Like, does it have a wave? Like, it has both effects because it's both in this superimposed state. I'm just saying, like, does the particle exist until you look at it?
I wish I could tell you, bro. I wish I could
I
tell
have
you.
a question.
Yeah.
So, when you say casually at the end, like the cat can be both dead and alive.
Yeah.
Do you mean this like parentheses probabilistically?
Well, that's the big question. That's a big question. Some people would say that it is actually dead and alive at the same time. Some would say it's just like that's a
What would that
probabilistic
look
model of
like?
it.
Like, what do they like theorize about that? Like, what would it actually be like?
It depends on the interpretation you look at. So we'll look at some interpretations and they'll have different ideas of what this means. Yeah.
Yeah, I think when Schrodinger first posed this, he actually used this as an objection to the Copenhagen interpretation because it
Yeah, because this seems ridiculous. Like a cat can't be both dead and alive. But
so this is supposed to be refuting instead of like an actual.
yeah, but it's also a good illustration because of its simplicity. Any other questions? Okay.
I was gonna ask, like, you drew the diagram and it's like the gun could kill the cat, right? If I hear the gunshot, am I measuring it?
So that's why you can let's say it's like poison, or let's say you put the box far away from you, and then you put on earphones. Like there's a way to set it up experimentally.
Arjun stuff. Like,
No. If Peter's watching this, no, I've not done that. Okay, now we get to the good stuff. Heisenberg's uncertainty principle, which I'm sure Heisenberg's a name you guys have all heard before. But no, it's not this guy. This is Walter White. This is not Heisenberg. But he took the name of the last name of Werner Heisenberg and made it his name. I'm sure you guys knew that. But I want to make that clear, and I hope this image like really illustrates the difference between the Heisenbergs. So the simple way to think about the uncertainty principle, which is our Heisenberg's uncertainty principle, which is a core tenet of the Copenhagen interpretation, is that it's not possible, it is impossible to know where something is and how fast it is going at the same time, right? And this, if we have more information about where it is, then we have less information about how fast it's going. And we express this mathematically through this inequality. Delta x, delta p is greater than or equal to h bar over 2. So delta x just means our uncertainty in position. Delta p means our uncertainty in momentum, which is just mass times the speed. So you can think of it as just uncertainty in place, uncertainty in speed. This combined uncertainty has to be greater than or equal to this constant h bar over 2. H bar, it's not the number isn't important. All that matters is that it's non-zero. So there is some uncertainty, but it's a very small number. So h bar is the reduced Planck constant, and it's approximately 10 to the negative 34 joule seconds. So it's really, really small, but there is uncertainty. And we can think about this like, let's say we do a measurement of position, and we know its position. Then our uncertainty in position goes to 0. But in order for this inequality to be satisfied, what that has to mean is that our uncertainty and its speed has to be infinite. If we know exactly where it is, we cannot know how fast it's going. And it's commonly thought that this is actually like a limitation of experimental capability. Like we're not good enough at measuring stuff. But this is actually like a fundamental property of the universe, a fundamental axiom of the Copenhagen interpretation. You cannot escape this uncertainty. Yes?
In that case, how is that like number specifically found or observed?
Mathematically, there's a derivation for it that you'll go through if you take quantum mechanics. But
H bar is like it's like a everything has like a quanta.
Mm-hmm.
He was talking about discretized energy levels. There's no like one like 0.1. There's only like 0, 1, 2. There's nothing in between.
Yeah, I
And
skipped
Planck's
that.
constant is like the smallest possible increment.
Okay.
That's
Yeah,
quantized.
I skipped this slide initially, but I would like to talk about where the like discretization of observable values comes from, and that's best illustrated with like an example and a derivation. But I'll do that at the end if I have time, if that's okay.
you have as much time as you actually.
I'm sure you would have, but I cannot say that about everyone else here. So I want to respect their time. Okay. So yeah, the reason why I said uncertainty principle and I made sure to make sure you knew it was Heisenberg's uncertainty principle was because this isn't the only uncertainty principle. There's actually uncertainty principles for a lot of different things. The second most famous would be energy-time uncertainty principle. It's the same uncertainty, h bar over 2, but it's same. It's not instead of position and speed or position and momentum. It's time and energy. But there's actually a generalized uncertainty principle that applies for any two observables whose operators do not commute. I know you guys don't know what that means, so let me explain. So, if you remember in the beginning on the slide that I mostly skipped, I said that if we wanted to like get an observable out of a wave function, it's like a transformation that acts on the function and it returns some value. You guys remember that?
Yeah.
Okay.
Yes.
Okay.
Well, yes, I do.
So now let's say we have two observables, Q and let's say H. So mathematically, this idea of commutation is that if the order of the measurements impacts the results, then those observables and those operators do not commute. So if I measure like Q, or I measure let's say H first, and then I measure Q, and I get some value, but then I measure Q first, and then H, and I get a different value, then those observables do not commute, right? The measurement of one impacts the other, so those don't commute. And if measurement of one impacts the measurement of the other, that's why we have uncertainty, and that's where we get like all these different uncertainty principles. Go ahead.
How much of this is like a statistical, since you're using like stats and probability as your method, since it's all like
Well, this is
statistics?
purely mathematical. This is just linear algebra.
Oh, so there's nothing to do with like mutually exclusive.
The uncertainty for the uncertainty principle, well, it arises as a consequence of the probabilistic nature, but it's this is just linear algebra.
Okay, I was just curious about any of your like mutually
Like,
exclusive and independence and that.
Matrix commutation is like it applies to any linear algebra field. Any other questions? Yeah.
Also, I just want to add, I just learned this in my Fourier analysis class.
Yeah.
So like you can prove the Heisenberg uncertainty principle like without any physics too.
Yeah. I think I might have actually an illustration here. Let me see. I guess it was on this slide. So I think that's what I was trying to show here. So another way you can think about it, or another way to, like, I guess conceptualize the uncertainty principle is like, I've shown that like if we have like a certainty of where a particle is, the function looks like this, right? If this is position here, this is what the wave function is. It's like the delta function spiked here. But we also need to remember, like when we're creating these wave functions, what we're doing is we're adding these different waves together. So if I want to create this function out of just like plain waves that look like this, and let's say they're different wavelengths, I need to add together a bunch of waves of different wavelengths in order to get this function, or to get this delta function, right? And the wavelength of the wave is directly proportional to its momentum. I think it's P equals, is it h bar over lambda? Do you remember?
Something like that, yeah.
H bar over lambda, where lambda is its wavelength, right? So if I have to add a bunch of waves together, different wavelengths, in order to get this, that means I'm adding a bunch of like things that have different speeds together. So that's where I have uncertainty in the speed. I don't know if that really illustrates it. It's probably more useful if you have some understanding of like Fourier transforms, but that's also a way that you can get it without the linear algebra. Okay, now to get into more, a lot of that was very mathematical. I'm sorry for that, but it's necessary to establish these concepts. But I think for the rest of this should be more theoretical and it should be easier to understand. So let's talk about causality. Like I mentioned it briefly in the beginning when I was differentiating classical versus quantum mechanics. So local causality means that an object is only influenced directly by that which is only influenced, I guess I shouldn't have included it twice. It's only influenced by that which is in direct contact with it. So if I have like two like particles or two balls.
I hope so.
There's no way.
Two spherical objects. The only way that
He said if.
object. Okay, is that, are we good? Get it out now. Get it out now, guys. I know. I didn't mean to. I wasn't thinking. If the only way that sphere 1 can impact sphere 2 is if it like hits it. That's yes. Do you know what that's called? Newton's cradle. The reason I say that is because I always thought it was called Newton's balls for a long time. And I saw it feels like Newton's cradle. I was like, what? But yeah, so local causality means that if something's something can only impact something else if they're in contact in some way, or even if it's like there has to be something that's mediating the interaction. Like I can impact Eddie if I like throw something at him, but there's still something there that is like carrying that causality.
It could even be like words, right?
Yes, sure. Sound waves. Yes, the sound waves.
It's only empirical phenomena.
But so not like, I love you, and he'll like come to you. That doesn't.
Well, my sound waves are impacting him, and he's
rendering it.
Yes, yes. So that's local causality.
And if you did this, like, it'd be like the photons to his eye. Analog.
If you had a supercomputer, you could actually just calculate all this.
Interesting.
It would know that you would.
I think love is as
Probabilities
necessitative
love Eddie and
as any empirical interaction. That's just.
Yeah. Anyways.
So this can't account for love, is what I'm hearing.
No, it can.
Okay.
Love.
But is it just like a?
Love does not violate relativity. Love travels at subsonic speeds, so we're good. And then, in distinction to the idea of local causality, we have non-local causality, which says that things that are not in contact in any way or not mediated, they can still have influence over each other. And before quantum mechanics and before even like classical mechanics, like forces were some of the most fundamental forces were like formulated as these non-local like actions at a distance. Like gravity, for example. People thought gravity was just like some abstract thing that like it pulls us together, or like electric forces, for example. But then these were later shown to operate in like local frameworks. In the case of gravity, like general relativity and the curvature of space-time, that's a local way to account for the effect of gravity. And Maxwell's equations allow for like the electrical forces to operate in like a field theory where they're particles or they're fields. Well, they're both. But yeah, so basically they were shown to operate in a framework of locality, and then it's like, okay, everything's working great. And that's before quantum mechanics. And then you get to quantum mechanics, and it all falls apart. So then we enter the Einstein-Podolsky-Rosen paradox. The paper for this was written in 1935, and it was one of Einstein's ways to like argue against Copenhagen interpretation and establish that it's an incomplete theory, and it leads to it describes the idea of quantum entanglement, where certain systems can become entangled in such a way that they can have non-local influence over each other. They cannot be in contact, but they can still have influence over each other. So yeah, quantum entanglement is just the idea of like the quantum state of one thing becomes dependent and contingent on another, and they remain in this state until something else happens.
Can I ask you a question on the?
Yeah, go ahead.
The quantum entanglement. This might be a little too technical. You can just not answer me.
Yeah.
They came out with this won the Nobel Prize like recently, I thought. And then this one, it was like 2022 or something. So even like when this won the Nobel Prize, they discovered like that spooky action at a distance, like actually didn't happen. I don't know if you know anything about that. Can I answer you later, David?
Yeah, maybe let's talk about it later.
Okay.
Are you headed out? Yeah. Okay. See you later, bro. Really good job. Yeah. Thank you. Thank you. Okay, Dave. See you later. Take care. Yeah, thank you.
How can we translate that data to all of it? So I don't know at all.
Yeah, go ahead, Mark.
When you're having these different paradoxes and theories coming together, what is within like the scientific field? What is way of like quantifying whether or not a theory is useful? Is it just a matter of it makes better measurements? Is
It's
it a matter of
explanatory
elegance?
power.
So it's just like if I have more elegant theory, but it's like slightly less.
Well, that's Occam's razor, so that's one way. It depends on what metric you're using to judge. Like, you can use a different metric to judge at theories.
Yeah, so I'm just saying you have these different competing theories over time.
Yeah.
So, and then this one I would imagine.
That's the modern way.
Well, let me talk about it, and
Okay.
then you might get some resolution. Did you have a question? Or you, okay.
Oh, no, it was just in line with that, where it was like, how can you, I guess, tell the like betterness of one over the other when this is all about unobservability? But you said you were gonna get into it.
Yeah, so let me know later if I don't answer your question. Okay, so originally the EPR paradox was done relating momentum and position and using that to show a contradiction, but later on David Bohm had a variant of the same experiment, which I think is like a lot easier to understand, so I'm going to focus on that for now. So our setup is as follows. We start out with some particle in space, and we're going to say it has spin 0. And all spin is, it's not really important specifically what it is, it's intrinsic angular momentum to a particle. What's important to know is that like you can either be spin up or spin down, and these are just values. It's not of critical importance. And this particle spin 0, it decays into two particles of spin 1/2 that then travel away from each other, opposite to each other, right? So the only possible value for these smaller particles are plus or minus 1/2. That's why we call them spin 1/2. And since we don't know if they're spin plus 1/2, which is spin up, or spin minus 1/2, which is spin down, right? The wave function for them is a linear combination of the two. And we can say, let's say they have equal probability. So the wave function for this particle in like the spin part of its wave function, which concerning its spin, is like 1/2 spin up plus, or yeah, 1/2 spin up plus 1/2 spin down. Because remember, Born's rule says that the probability of it being in spin up is this coefficient squared, so that would be end up being 1/2. Yeah, and the same thing for this particle. It also has the same wave function, but it's traveling in a different direction, right? But we actually have some more information about this. Because we know it started out as spin 0, we know that if one particle is spin 1/2, the other one must be spin minus 1/2. And this is just because of conservation of angular momentum. Right. Yeah. So we have this idea, we know that the wave functions for each, but we know that if one particle is spin up, the other has to be spin down, right? So let's say we let these particles travel an arbitrary distance, however far, and one particle we measure to be spin up. Let's say like the left one. What do we measure for the other particle if we measure it directly after?
Does it have to be spin down? Like, is it similar to the thing where you were saying where it's 100% likely at either half, like it's the Schrodinger's thing where it's like both at the same time, therefore like it necessarily is the second one?
That's the right answer, but I think the reasoning is, I don't know if the reasoning's all there. It's not exactly, but it's because of the conservation of angular momentum. If we know the first one is spin up, so the whole system, the total spin is conserved. Overall, it has to be 0. So if we then see this as 1/2 over here, this has to be minus 1/2 in order to conserve and keep the total to be 0. Does that make sense? I don't know if that was what you were trying to say.
That makes sense.
Was that what you were trying to say?
Pretty much, yeah.
Okay, go ahead.
I know this happens with like electrons, right? But is that two particles? Or this is one particle?
This is one particle that decays into 2.
So this is not like electrons, because electrons are two particles that are doing this in a dance, right? Or am I thinking about this wrong?
Yeah, this isn't like an atom, like the electrons orbiting on
This is
nucleus.
within an atom.
No, these are not.
These are just,
No.
This is like
This is like a particle. This is like,
So it could be like like neutron decay into like a proton and
Yeah,
an
yeah,
electron,
that-
and you have to maintain spin within the
yeah,
system.
it's not very important what they are, but
Yeah.
they decay into two particles of spin 1/2
It has to
that
be-
travel
Instead of
Unless
energy,
it's
you're
zero.
conserving spin
Okay, that makes
and
sense.
angular momentum in the situation.
Mhm.
But
Because you
Is-
observed it
is
at,
that
at
okay?
a moment.
I didn't,
therefore-
I still don't fully understand. Like, I have
No,
a
there's
class
not.
that
Sorry,
delves
this
into this
is
a bit,
like
like I read
time one,
interactions,
and
like
then
radiation
there's
interactions,
phase
touches on
time
this,
two.
but I'm still like.
So it becomes
Yeah, I'm
two.
not
So
taking,
this
I
has
mean,
to
I'm
do
an
with
English major, I don't.
Yeah, it's like I'm still like I felt like I'm still out of my depth.
Okay.
You can do this is like a neutron or something.
Because I know in orbital theory, you know, the electrons have the spin up, spin down.
Yeah, so that's around an atom.
That's
Electrons-
different. That's different.
This is a
Similar,
different
but
thing.
different.
That's just a different scenario entirely.
Okay.
But spin applies to electrons. Electrons have spin.
Yeah.
All particles have spin. This is but we can have bigger particles that become smaller ones. So we can have a bigger particle that's spin. It's actually spin 1 because that's the maximum possible spin it can have. But it can have 1 spin or 0 spin or -1 spin. But we call this a spin 1 particle. And spin 1 particles can decay into small ones that are spin 1/2. But those are only plus or -1/2.
Is this how you get like quantum entanglement, where if you have one that's been
That's exactly
that's
exactly what I'm trying to demonstrate here.
I see.
Right. So we can think of these two particles as being quantumly entangled, right? Because the state of this one directly impacts the state of the other one. If we know that this one is spin up, this other one has to be spin down to conserve angular momentum. Then they're quantumly entangled. No matter how far apart they travel, this could travel like 10 billion light years in that direction. If we measure its spin, we will immediately know the spin of the other one. And go ahead.
How much is it of you just looking at one instance of a particle in terms of measurement? Like if we have like tens of thousands of particles and then we're just observing, like, do they all have to be like dependent on each other? Like that's where I'm like,
Well,
if we expand this out to like instead of one particle and you do tens of thousands of measurements.
Well, then your
Like-
wave function changes. Then, like, your wave function can describe a system, right? So those 10,000 particles might share the same wave function, right? If they're all in proximity. You can also have a bunch of that are quantumly entangled like this. So like, yeah, this could be more than 2.
I guess I'm just prodding my question is how much of entanglement is dependent on the fact that you're just focusing on one particle and one measurement and having to conserve it in the system, versus if you expand the system and expand your universe and system of like control volume that you're analyzing, then you'll see that not everything is necessarily entangled and it's merely just
Like
having
one
to
thing.
satisfy angular momentum in the system. So like all I'm just saying is, with this point of view, you just have one particle in this system. If you expand it out to 10,000, and you have all these decays that they're not necessarily entangled. It's merely just a matter of what your control volume is of measurement.
Well, we consider that entangled because they're over such like a great. You can take them over any amount of distance that they cannot like have any effect on each other. Like essentially 0 effect on each other, right? So this is the whole idea of what quantum entanglement is that even across time, even across space, these things can be connected to each other. You can't have that locally without some sort of mediation. If I take this 10,000 billion light years away, and then, well, actually I'll get to that on the next slide. So that might help.
Okay, I was just saying how much of it is your system and what you're controlling for and having to conserve angular momentum in the system, and how much of it is just
Well,
because it's one
the
particle.
conservation is what leads to the quantum entanglement, the necessity of the conservation.
Yeah, I was just saying if you have 10,000 particles and you have to equalize angular momentum in the system, that like A particle and B particle from C particle, if I have like the whole alphabet of particles, they're not necessarily entangled with each other. It's merely just a matter of measurement of having to regress back to angular momentum. But we can talk about later.
Do you
I don't
ever
want to.
answer like the answer? There is an answer to a paradox as of like a few years ago. Do you answer it?
Yeah, you'll see.
If it's not, if he's trying to posit an answer to the paradox, if it's not that, then it's something. It must be the answer. There's an answer to the paradox, and you're positing an answer.
Is this like critical right now for your understanding?
No,
If
I'm
not,
saying,
I'm-
I'm asking if you're covering the answer to the paradox. Then that answer.
Well, there's different answers.
Okay.
It's like this is not like a
You said it
question.
solved though.
I think they solved. It was a Nobel Prize like a few years ago. Like I always
Okay.
can guarantee it.
Well, we can look at that later. Is that okay?
Yes, of course. I was just wondering because it answered Mark's question.
Okay. This is Eddie. Do you have a question?
Oh, no, I was just gonna go deeper into that, so we'll.
It's after.
Because if you just
They don't say that.
So right, the answer is to the question. You measure the first one spin up, what's the spin of the other one? Spin down, the 100% probability, right? Or even if you measure it to be spin down, the first particle, the other one would have to be spin up. Necessarily, you have to have opposite spin to conserve the angular momentum, right? And this result tells us that the measurement of the first particle instantaneously influenced the state of the second particle even though they were over an arbitrary distance, right? And this, at least they claimed that this result was a violation of relativity, which says that nothing can travel beyond the speed of light. So this is the paradox, as it was proposed by Einstein, Podolsky, Rosen. So then they tried to create their own idea for how we could resolve this paradox and why Copenhagen was wrong. They said Copenhagen was wrong because of this result, and then they tried to give their own solution to how you can make quantum mechanics work without this idea of non-locality. So then we enter into hidden variable interpretations of quantum mechanics. The first one was kind of posed by Einstein in this paper as a response. And I'll read a quote from him. He says, "Quantum mechanics is very worthy of respect, but an inner voice tells me that this is not the genuine article after all. The theory delivers much, but it hardly brings us closer to the old one's secret. In any event, I'm convinced that he's not playing dice." So I'm sure you guys have heard like God does not play dice. Most people think that like has something to do with like fate, but really Einstein was talking about quantum mechanics when he made that claim. So he just rejected the probabilistic nature of Copenhagen quantum mechanics, and he said that the wave function was incomplete, right? Or at least the wave function does not completely describe the system, whereas Copenhagen said that the wave function is all you could have. It was a complete description of the system. And he proposed the idea of hidden variables, which is that there's something that is not the wave function, some variable, or maybe multiple variables that we cannot know, hence hidden, that in combination with the wave function, or instead of the wave function, could completely characterize the system. And for this reason, it's not probabilistic. Now, if you can know everything about the system, then you have determinism. And at least in his hidden variable interpretation, he said that this could lead to local causality. And there's no idea of superposition, right? It was not, nothing could be in a state of, nothing could be in multiple quantum states simultaneously. It was always in one state, but we just didn't know because we didn't know the value of this hidden variable. So this idea of hidden variables, his interpretation, he claimed that it resolves the EPR paradox, right? Because now, instead of like spin up and spin down states, or the wave function being collapsed over some arbitrary distance, there's no idea of wave function collapse. This is no longer probabilistic. It always had the spin that it had depending on this hidden variable. So he said that maybe there's some hidden variable like called mu that was in the initial particle before decay. And depending on this value of mu, that determines the spins of the particles at the time of decay. So like let's say if we have mu equals 1, then this particle becomes plus 1/2 and this one becomes minus 1/2. So in that way, the information isn't being, there's no non-local causation because this information is being transmitted at the time of decay, and that's definitely local, right? It's decaying, it's in contact, it's directly causing and determining the spins, not across space, but at that point in space and time. And there's no idea of wave function collapse. So for that reason, relativity isn't violated. There's nothing being transmitted instantaneously across an arbitrary distance, and then he thinks, okay, everything's working now. Until Bell's theorem. And I think this might be what you're talking about, but this wasn't recent at all. But this is the, okay, it probably wasn't this. Go ahead.
I have in my statistics world, we say like mu is an average. What is it in this case?
Sorry?
We say that we call mu like an average. Like
Mu is just a variable. You could call it eta, you could call it x, you could call it y. It's just a hidden variable.
The Arjun variable.
Yeah.
Wow.
Anything.
This is perfect.
Yeah, that's actually why I chose. That's really why I chose me.
Wait, why'd you choose me?
So everything's working with hidden variable theories, Einstein says, until 1964 with John Stuart Bell and Bell's theorem and the related Bell inequality. So there's actually, it's not like a theorem, it's actually like a bunch of results that show that quantum mechanics, the results are incompatible with the idea of like a local hidden variable theory. There's a bunch of math behind it, but basically he just like proves that if a hidden variable, a local hidden variable theory were to be correct, it would have to satisfy like a mathematical constraint that's called Bell's inequality. And then he showed that through experimentation that and prediction that quantum mechanics, or like in reality, this inequality is not satisfied. So we cannot have a local hidden variable theory. But we could have a hidden variable theory, but it would have to have non-local causality. So basically, Einstein was wrong, as per usual.
We gotta rip in the chat. One stone.
So then some of you might ask, like, okay, well, that's what Einstein had to say, but how did the Copenhagen school respond to the EPR paradox? And they basically just claimed that since you cannot like choose the outcome of the measurement, you can't cause the wave function to collapse in a certain way, you couldn't transmit any information using a setup like this. Like I couldn't make one particle collapse to spin 1/2 to make the other one across this infinite distance or arbitrarily large distance to transmit some form of information. So no information is being transmitted, so there's no violation of relativity. So that's how they respond to the EPR paradox. What's up?
They're saying, go back. Which caused the wave function to collapse, or it had already been collapsed that state by measurement of the first. Oh, okay. So
Yeah. So
they're saying that because you cannot determine that the other particle is truly at that.
yeah. So like let's say like the particle's here, and like there's some person A for Arjun. He's measuring the first particle, and then we have person B, whose name has a B here, Blake.
Fine, go the Blake variable.
Right? It's like
a particle.
there is no way that Blake could know. Like let's say I do my first measurement, but Blake doesn't know that. He cannot know that unless it's by means of like subsonic communication. Like I can't convey to him that I've collapsed the particle faster than the speed of light. So that's not a violation of relativity. So when he does his measurement and he says spin 1/2, he has no way of knowing that if the wave function collapsed when he measured it or had already been collapsed by my first measurement, right? Does that make sense? So there's no violation of relativity.
Oh, yeah.
So you're saying the wave function itself stretches across all like light years, and then therefore it's intrinsic to itself because it's already been measured once. I don't know if I believe that.
What do you mean intrinsic to itself?
You say basically if I have the decay particle A and B, they're entangled by the same wave function. So if I measure it at A, I have already peaked the wave function, therefore doing something to particle B.
Well, okay, we can look
because
at
they're the same, but even though they're so far away, it just stretches infinitely.
Yeah, so the wave function collapses.
It collapses at A
simultaneously across. Yeah.
So you're saying the wave function can just stretch indefinitely.
Right.
According to this.
Sounds like the ether, bro.
Sounds like I don't believe it. So wait, isn't a particle spin? Isn't a particle spin superimposed, like at all times until you measure it?
Superimposed?
Yeah, like isn't it like if I have two electrons, they're both simultaneously 1/2 and negative 1/2 until I measure it.
Yes. Yeah.
So
right. Well, no, it depends on the system. In this system, yeah, we get a different system where the spin has some other value, like.
Right. I mean, like
right.
the superimposed, like that's what's
yeah. So before, at the time of the decay, the claim is that okay, these are both in a linear combination of spin up and spin down.
Right.
And then measuring one collapses that one and collapses the other simultaneously.
I don't know. I feel like the one wave function theory does violate relativity, but.
Well, that's what they claim, but the thing is, like, what's violating relativity? What's traveling faster than light?
No, I just think that one wave function can't stretch that far.
Okay.
That's I don't know. I was just talking.
No, bro.
Well, even if they have several wave functions, right? That like it doesn't signify that they're quantumly entangled. The wave function is just a representation. It's not an actual thing. It's just a representation. So the wave function is just a conceptual way of like relating information. So why could it not stretch across time? There's there's some theories. Actually, we're gonna get into it here. Is this no? On the next slide rather. You'll
Yeah,
see.
I made you go back a slide.
Okay, no worries.
I
No
don't know if
worries.
you remember that.
Well, now I know.
You didn't know that before the wave function collapsed.
So as Bell's So as Bell's theorem showed, we cannot have a local hidden variable theory, but we have hidden variable interpretations that are non-local, and the most influential of these would be the de Broglie-Bohm interpretation, which is also called the pilot wave theory. So this is actually directly what you're saying. Instead of the idea of having like separate wave functions for each system, there is a single wave function that describes the entirety of the universe, right? And this theory, but in addition to this idea of a wave function, is a hidden variable theory. So there's something more. So it actually posits that there is an actual configuration of the entire universe that can be known, and that we can know even how it evolves over time as well. So we get back, this theory is deterministic. Yeah, go ahead.
Just so I can make sure I'm understanding you correctly. So you're saying like the whole universe is just like a whole huge plane, and you have these like peaks essentially along it, and all these peaks are determined by this wave function. And this wave function is like what, this hyperdimensional quality dependent on like
it is hyperdimensional.
Like, to like the 20th like time, energy, etc., momentum, all these different discrete things.
Yeah, but
and
the
it's
difference
just like what is that what you're presenting to stay?
Let me go to the next
just
slide.
So I can understand.
There's a lot of questions.
So the pilot wave in the de Broglie-Bohm theory is not the same as like the Copenhagen wave function.
Okay.
And that the pilot wave is actually something that exists in reality and has influence over like particles.
So it is dependent on like displacement and time and momentum.
It's not dependent on that. It's the cause of that. The pilot wave is the cause of that.
So it's
So
you're gonna have, okay, can you clarify?
maybe let me talk a little more about it, and then
Alright.
maybe you'll.
Because I thought I understood, but I guess I don't.
So
I'm telling you.
well, I didn't go too much into depth, so I hope I can answer your question. So the pilot wave is something that exists in reality, has influence. It creates what Bohm calls a quantum potential field, which is, it's like, I don't know who gives it such a weird name. It's basically just some way of describing all the forces that are acting at all times.
Oh, that's what I thought I was saying. It's just you're just like having all the variables in the universe like all just broken down into one variable.
Yeah, but
and you're just it's a function of like
time
20.
and of every particle.
Okay,
every
then,
particle.
yeah. Okay, then I thought we were saying the same.
Okay, sorry, I didn't.
I was confused. Okay.
Right. So yeah, again, and the difference because this is universal, right? This every single particle in the universe is considered in any quantum analysis. So we have a universal wave function. You can look at subsystems of it, but you cannot. You have to factor in everything else when looking at that system. Go ahead.
How is that non-local?
How is that non-local? Because you can have this same effect of the pilot wave can change particles that are not in direct contact. So
Isn't it in direct contact with every particle?
Because if everything's
Wouldn't
connected,
that localize everything?
depend on like.
That's what I'm thinking.
Depends on what is
It's like
local?
definition of
I think it's like a
That's what I'm confused about.
definitional thing.
Everywhere.
Okay.
So yeah, that's actually a question I had to because I thought like this seems like a local one to me.
Okay.
But it doesn't violate like the relativity. Go ahead.
How did you posit this? 'Cause this sounds like on the level of pre-Socratic saying everything is actually water. Like this sounds really unscientific. And so is there actually like a lot of math behind this?
Well, it's
that
not.
you're
It's not as
seeing?
easy as you think because like what?
Or is he
Like if we have an understanding of
writing
gravity, we have an understanding that
Oh, can you explain gravity?
Please no.
I don't think
That's an explanation, an example.
I didn't promise an explanation.
Oh, that's the Socratic.
You say all
I think this idea of everything being connected in one, that's what leads to this conception. This is just a scientific formalism of the connectedness of everything, or one way to do that.
It just seems like he's positing something that's quite impossible to prove.
Nothing.
Like, that there's this theoretical, not even theoretical, it's not universal theory of everything with an unfathomable amount of like hidden variables or
there is proof of it through these examples. Like this theory explains like the double slit experiment. The EPR paradox, it has its explanatory power.
It's
So there's been objections to it, obviously, but we don't know if it's correct or not, right? But
We can't do that. And then
it does provide explanatory power over what we observe in reality.
Everything
Dip into the level of
The Big Bang was a complete unknown that we can solve.
Well, it is a hidden variable
What would you
theory,
say?
so
Yeah.
part of it.
I would say like
Variable,
That makes sense.
Yeah, sure, but.
But yeah, so another important thing is that like we have the idea of wave function. Yeah. Can we bring it back together, everyone?
That's an impossible question to solve.
I promise I'm almost done. Sorry for taking much of your time. Can we finish strong, guys?
Yes.
Okay, thank you. Thank you, Chase. So
I think you should just like go like finish it without like a single question interruption.
I think let's just continue on. So
You just have patience.
So, unlike the Copenhagen wave function, we do not have the idea of wave function collapse. Like this pilot wave, it's a real wave in reality. It doesn't like collapse the same way our Copenhagen wave functions were. But, like the Copenhagen wave functions, it is also governed by the Schrodinger equation. So we can know how this pilot wave changes and evolves in time. And we know that the pilot wave is actually responsible for determining how particles, the trajectory of particles across time. So we can know what causes it and we can know how that changes. All that's missing is we do not know how it started. So the hidden variable in the de Broglie theory is actually the initial configuration of all particles in the universe, right? So if we had that information and we know the pilot wave and we know how it changes, then we would know everything that there is to know, right? So that's where the determinism,
Empirically or like whatsoever?
like whatsoever. You can know where every particle is at any point in time,
Whoa.
forever.
What about like what's transcendent of like the material world?
Um,
Like know about that?
Maybe.
Like, what about like
No thoughts
what
there.
about like apophatic theology?
This is why I don't believe it. Wait.
Go ahead, Mark.
So just to clarify, in your first slide, when you're defining quantum mechanics and everything, it was defined by like non-determinism, very like stochastic and probability.
Yeah, correct.
This seems to basically say the exact opposite. Everything's
Yes, this is a
deterministic.
different
So-
interpretation.
Okay, so just to clarify though,
This is not
that's
Copenhagen.
going against, yeah, so I guess
Yes.
unorthodox.
Yes,
hence-
this
yeah.
is This is a hidden variable theory, right? It's trying to create, it's trying to like bring determinism back into like determinism to explain.
Just so I could clarify how it deviated from the orthodox.
No, I got you.
All right.
So I just want to clarify for myself how deep this determinism goes, and I think that's like what the questions before were is like